So, pardon? Oh yeah. We've learned that, like, we've talked about nuclear reactions and like beta decay, alpha decay. So it's like that one reaction happens, but then we've kind of alluded to it in some of your workbook questions and stuff, that the reaction can keep happening. So it's like you have a daughter element and it goes through the decay again. Okay, so it's like each time there's a decay, it almost happens again, which results in this kind of concept of a half-life, which we've talked, you've kind of heard the idea of half-life before, especially when we're talking about like radioactive dating and stuff with fossils. We talk about what's its half-life, or what's that rock's half-life to determine the age of the fossil. So the half-life, its definition is the time required for 1/2 of the radioactive nuclei in a sample to spontaneously decay. So it's, yeah, the half, it applies to the 1/2 of the actual sample has been decayed. So it's like the original parent has decayed into other daughter elements and other particles like alphas and betas and stuff. So the half-life is specific to the type of radioactive material, i.e. different elements. Each have a unique / different half-life. So like some radioactive elements, it might like take 200 years for half of that original to decay. So like carbon-14, it's like a long time period. But for, I don't know, something that's just more radioactive, it could take a half of a second, So it's extremely variable. And okay, so the number of nuclei of the original isotope left in the sample after the given amount of time can be calculated using this equation. So we have n is equal to n naught times by 1/2 to the power of n. So you do have this one on your formula sheet, so let's just note where it is. So it's under atomic physics. It's the only one that we haven't actually done yet under atomic physics, so you can see it there. So where n is the amount of material remaining after, so it's kind of, so it's like what you started with, how much is left afterward. N naught is the original number of the sample before the decay started. And n is the number of half-lives that occurred over this given time. Now, in order to get n, you usually have to use this formula that t is equal to, n is equal to t divided by t half, where t half is the half-life. It's not like half of t, it's the half-life. Okay, so don't go like t times, it's not t times a half, it's the half-life. So this though is not on your not on data sheet. So this is one that you kind of have to memorize or just be aware of. But you can kind of, if you think about the definitions of each of those variables, it's logical what the formula is. So it's the time given divided by the half-life gives you the number of half-lives. Okay?
So this is very the little n, that's the power?
Yeah, the little n is the power, yeah. Now, the amount of radioactive material can be expressed in different units, okay? So, and this is really important to notice. So, it can be expressed in terms of mass, like how much you measure, the number of atoms, the percentage, the decays per second, becquerels, counts per minute, or activity. So, if you're told, like, the original sample, its activity is blah, blah, blah. Its activity is n naught. and it's the amount of activity afterward is n. So, or it could be like the original mass is this kilograms, and then what is its mass afterward. So it can be in all sorts of different units. The only thing that you need to make sure is that n and n naught are recorded as the same unit used. Or same type of unit, same unit, whatever, yeah. And this is because, like as I said, the radioactive materials have such varying degrees of their half-lives and like how they decay and what they're like, and so we have to, it's good to have a formula where we can use all sorts of different units to kind of compare things. So I'll show you examples of that too, but just keep in mind if you get really weird units, it's okay as long as they're the same for n and n naught. Okay, so we're just going to analyze these graphs a little bit. I'm going to put in some writing in here. I'm sorry I didn't give you very much space there, but we'll just try and write around the graph, even though I didn't give you too much space. So say we look at this graph. It says activity counts per second. Okay, so that's like whatever units. Okay, so this is like the units of n naught. Right, like it's just, and the units that it gave us is the activity counts per second. So what we see here is like this is like what we're starting with, so it's like times 0. If what we're starting with, this must be then n naught, because that's the original amount. Okay, and then what we have on this graph here is our leftover and what we are left with. So if you think about it, this is like the parent element. This is what we start with and how much of it we have left when we're done. So if we kind of compared and thought, how much daughter element am I making when I go through this reaction? Well, I would start with 0 daughter element, right? And as the time goes on, that it will be like kind of like the opposite type of curve. So this is a question in your workbook, is where you have to think about kind of what would the daughter element graphs look like comparatively. So I just wanted to kind of let you know about that. Now, another thing that we can kind of analyze from this graph is half-life. We can look at the graph and actually determine the half-life just by our observation. So say, really, what you can do is you just look at any beginning amount. So say we start with the 80, and you take 80 divided by 2, and look at how much days has passed to get there. So to get to 40, because that's the half of the amount, okay? It's harder to see on my whiteboard here, but what does that look like? About like, it almost looks 5.5, hey? Yeah. So it'd be like 5.5 minus 0 is like, well, I don't know, maybe it's more than that. I think it's like 6, maybe even 6, hey?
I don't know, let's rate them.
Yeah, 5.5. Okay. So using that data gives us about 5.5 days is equal to t half, right? Like half, because it's half-life. You can start and end with anything though. So say you wanted to start with how much do I have at 60 days and look at how much you have at 30 days and calculate the half-life. You're going to have a little bit different results depending on what you choose though, because of the nature of the curve. But it's an approximate value, okay? So let's look at this graph now. So this one we have the percentage of original isotopes remaining and their half-lives. So on this side, it's like some measure of n. It didn't really say. It just says it's like percentage. Okay, so percentage, and it's like whatever units it gives us to. Okay. Now here is our original amount. So our NO. But then look at our x-axis for this. For our x-axis, we're given half-lives instead of just time. So we can't figure out like t half from this one because this is just the number of half-lives. So it's like, okay, to go from 100 to 50, they had to use like 1 point something half-lives. Okay? So you can't really find t half from this, but it does give a good representation of kind of the same, it gives you the same curve pretty much of what's going on.